No? Here. Yeah, well, we got a job.
Okay, similar area. That's what we're going to do.
Oh, yeah. So if you better look at my schedule. You better look at it.
And you're right,
That's the Disney line. That's my office. He was in our building. Okay. That's something.
Good morning. Please be seated. Welcome to the QSR research session. And this is a very special session because all the papers are peer reviewed, and they are selected from 16 papers. Okay. So today we are going to have 4 speakers, and each speaker will have about 20 minutes to present, and about 3 to 4 minutes for the questions and answers. So because Xiaolei is going to have another session, so he will present first. So the first speaker will be Xiaolei Fang from Georgia Tech, and he will talk about the review user for life prediction using the degradation image stream interface.
Good morning, everyone. Welcome to my presentation. My name is Xiaolei Fang. I'm a PhD student from Georgia Tech. And this is a joint work with my advisor, Professor Cameron Campbell and Professor Maggie Gabriel. So my talk today has 4 sessions: the motivation and challenges, the prognostic methodology, the numerical studies, and the summary. As you know that nowadays there is a growing trend to use image sensing technologies for condition monitoring because they are non-contact and thus it's easy to use. For example, for some applications, the temperature is too high that the traditional contact sensors may not work. Okay, and the other reason that the image sensing techniques can provide image streams usually contains much richer information than other traditional sensing techniques. And if the image stream contains the degradation information of a system, we call it is a degradation image stream. As an example, this test bed in our lab is designed to run degradation tests for bearings. And with the degradation of a bearing, the temperature of this motor will going to increase, and it can be used to indicate the degradation level of the bearing. So if we use an infrared camera to monitor this motor, we can get this image streams over time. And this image stream contains the degradation information for the bearing, and thus can be used to predict the lifetime or failure time of the bearing. So let's say that we have a data set, training data set that will run n such experiments. That is for bearing 1, we run it from brand new to failure, so that we have its degradation image stream and its time to failure, or in short, TTF. And for system 2, we also run from new to failure and get its degradation image stream and its time to failure, and up to system N. And we are interested in finding out the relationship between these image streams and their TTFs. After finding out this relationship, we can monitor running its systems to get their in-time degradation image streams so that we can predict when the system is going to fail. Okay, so the objective of this talk is that to use the real-time degradation image stream to predict the residual useful lifetime of a system. Here are some literature regarding this problem. And you can see that most of the existing models for degradation modeling or IOL prediction are developed for time series-based degradation signals. When it comes to image streams, there is no work for using the image stream to do the IR prediction. And there are a few works to use image streaming for degradation modeling, use the spatial temporal models. However, that spatial temporal models is hard to be extended to the purpose of the IOL prediction. One reason that it's hard to define the failure threshold for spatial temporal process. And the other reason that it's hard to use spatial temporal process to do long-term prediction. So in this talk, we're going to develop a model to use the image streams to predict the IOL of our system. But this is quite a challenge. One challenge is that image streams have very complicated spatial temporal correlation structure. And for each image, the pixels inside each image has spatial correlations, and the pixels among different images over time has temporal correlation. So we need to capture such a spatial temporal correlation structure. The other challenge that is hard to define is failure threshold. As I mentioned earlier, for most of the existing models, they work with time series degradation signals. For such signals, when it crosses some threshold called failure threshold, it is considered to be failed. But for image data, it's hard to define such a threshold. And the third challenge that is dimensionality. As you know that image is always high dimensional. And if we have image streams, the dimensionality is even higher. So to address these challenges, in this talk, we developed a model called the tensor-based location skew regression with low dimensional learning. And to address this first challenge, we use tensor to capture the complex spatial temporal structure. And we use this regression to address the second challenge, that is, we do not need a failure threshold for this prognostic model. And we use low dimensional learning to address the third high dimensional challenge. And in the following several slides, I'm going to introduce what details about this tensor regression model. But before I do that, let's start with what a tensor is. Basically, a tensor is a multi-dimensional array. For example, a one-dimensional tensor is a vector. A two-dimensional tensor is a matrix. And the tensors with 3 and higher dimensions is called high-dimensional tensors. So the degradation image stream we introduced here is a 3-dimensional tensor. Now, you know what the tensor is. Let's look at how to use the tensor to build a location skew regression model. This is a location skew regression model where the response y is the TTF or the log TTF, the mu I is the location parameter, and the sigma times epsilon I is the noise term, and sigma there is called the skew parameter. And this model is widely used in reliability engineering, and it includes a lot of specific distributions, like a normal, not normal, logistic, log logistic, SUV, and Weibull. So when it comes to the tensor version, the location parameter can be expressed using this equation. Alpha here is the intercept, S of I is the degradation tensor or degradation image, and the B is the coefficient tensor you want to estimate. And the dimension of the coefficient tensor B is the same as the dimension of the image stream or image tensor, which usually is very high. The equation here shows the number of parameters in that coefficient tensor. If we say the dimension of tensor is I1 by I2 by ID, and one example, the 2 here represents the intercept and the skew parameter, and this part is the number of elements in the tensor. Okay, so as an example, we have 20 images, and each image has 20 by 20 pixels. So how many elements are there to estimate? It's 8,000. So you can see that it's a very large number. And given the fact that the sample size is very limited, so it's hard to estimate this model. So what can we do? We can use the fact that tensor images usually have a low dimensional structure. So we can, instead of using the whole dimensional data, we can do some dimension reduction. So how to do that? We can use this proposition. Basically, this proposition says that if the image tensors have a low rank structure in a low dimensional tensor subspace, we can project that tensor to that subspace to get a projected low dimensional tensor. And also we can project the coefficient tensor to that tensor subspace, also get a projected low dimensional coefficient tensor. And the inner product of the original tensors equals the inner product of the projected tensor. So we can use this effect to reduce this original regression model to be this one. And the number of parameters is accordingly reduced from this one to this one. As one example, if the original tensor is 20 by 20 by 20, we have 8,000 parameters. If the projected tensor is 10 by 10 by 10, then we have 1,000 parameters. So we can see that we use some dimension reduction techniques. The number of parameters of this model can be reduced a lot. But even after reduction, we can see that the number is still huge. It is very possible that the number is little because here is the P1 times P2 times P3, etc. So what we can do, we can use some multilinear dimension reduction on the coefficient tensor. So for example, use CP or Tucker decomposition to decompose this coefficient tensor. So instead of estimating the tensor itself, we can estimate these decompositions. So in the following slides, I'm going to first introduce what the CP decomposition is and how to use it to further reduce the number of parameters in our model. So a CP decomposition says that a high dimension tensor can be decomposed to be a product of several matrices, basis matrices. For example, the tensor with dimension P1 by P2 by P3 can be decomposed to a low dimensional matrices P1 by R, P2 by R, and P3 by R. And R is usually a small number because the data is spatial temporal correlated. And as one example, if the original coefficient tensor is with dimension of 10 by 10 by 10, which have 1,000 elements, and if you assume this rank R is 2, how many parameters are here? Is 60. So instead of estimating this guy, we can estimate this matrices. This will reduce the number of parameters a lot. So the problem is how to rewrite the regression model in terms of these basis matrices. Here is the solution. And let me remind you that the parameter we want to estimate is the intercept alpha, the skew parameter sigma, and this basis matrices B1 tilde to BD tilde. And this problem can be solved by maximizing the following log likelihood function, parallelize the log likelihood function. We add a penalty term here to spare sparsity and to avoid overfitting. And this optimization problem can be solved by optimizing one block of the parameter at each time. And we do this iteratively until it converges. So let's check the detail how to estimate only one block of the matrix. So let's say we want to estimate the Bayesian matrix of BD tilde. And this proposition said that the original regression problem can be simplified to a simpler regression problem here, with the block BD as the coefficient we want to estimate. But this problem is not concave. So to address this challenge, we do some transformation, and we can show that after doing the transformation, the problem can be transferred to be a concave one if the PDF function of the location skew distribution is log concave. And unfortunately, for most of the location skew distributions, their PDF are log concave. And even if they are not, it can be transferred to be a log concave ones. For example, the Bible is not log concave. But if we take the logarithm of the TTF, it can be transferred to a SEV distribution, which is log concave. Okay, this means that we can solve this problem using many existing methodologies like the block coordinate descent. So we summarize the blocks, the whole algorithm called the block relaxation algorithm here. And basically here shows that each time we will update one block until converges. So this algorithm have a global convergence property that says it converges to a stationary point from any initial points. And for this algorithm to run, we need to know the rank in advance. And we use BI to select the rank here. So far, I have introduced how to use CP to help to reduce the number of parameters in our model. Next several slides, I will introduce another tensor decomposition, the Tucker decomposition, how to use it for the same purpose. So similarly, the Tucker decomposition said that high-dimensional tensor can be decomposed to be a product of a small-dimensional tensor called tensor and some low-dimensional factor matrices. As you can see that if we estimate this guy instead of the tensor itself, the number of parameters can also be reduced a lot. So similarly, this problem can be solved using parallelized MLE, and it be solved using the block relaxation algorithm. So I just skip this part because it's very similar to the CP part. So next, let's see some numerical studies. First, we do a simulation study from a heat transfer process. And here is the simulation parameter, and we added the noise to its pixels. Adding noise to its pixel, and we generate 1,000 data for 1,000 system. We use each system have 10 images with the size of 21 by 21 pixels, and we use 500 system for training and the rest of 500 for test. And we generate two types of TTFs. One is from CP decomposition with ramp 2, and the other one from Tucker decomposition with ramp 212. And we add the SEV distribution noise term, and we evaluated the performance of the model using the test data and calculate the protein adders using this equation. So for benchmarking, we use a function PCA because it is very popular for processing the high-dimensional data. So how to do that is first we transform the tensor image tensor to be a profile by taking the average intensity of each image. And next, we apply FPCA to the time series signals to extract features, and then we do regression. I think we regress the feature to the TTF. We use a location skew regression model under SEV distribution. Now for our model to work, we need to first select the distribution, the rank. We use BIC here. We can see that BIC for both the CP and Tucker regression, BIC chose the correct rank and the distribution. And you may notice that for the Tucker one, there are too many possible rank combinations. So it is very time-consuming to select the rank and distribution. So we developed a procedure that can be used to automatically select the best rank for this model. In our paper, I'm not going to introduce too much detail about this automatic rank selection. And here is the partition adders. This one is for CP, this one is for the Tucker. You can see that both the CP and Tucker performed better than FPCA because FPCA use only the temporal information but lose the spatial information. Our model can capture both. And we can see that for Tucker, the auto-rank selection procedure works similar to the procedure for BIC selection. And next, we show a case study use the dataset from a degradation test from rolling element bearings. And each image is 40 by 20 pixels, and the failure time is between 15 to 55 minutes. And we use a leave-out course validation to test the performance of our model. And for each test signal, we do real-time prediction. That is, when observe new real-time signals, we can predict its TTF, use CP and Tucker decomposition, and calculate its their prediction adders. And you can see that in the case study, the Tucker works better than the CP, especially at the beginning. So I summarize the prediction adders using two figures. This one is the mean of the prediction adders. The X is the observation percentiles, and the Y is the absolute prediction adders. And this one is the variance of the prediction adders. And you can see that all these models also have a better prediction adders when times goes higher. That's because we have more observations from a system, so we can make a better prediction. The other observation is that both CP and Tucker works better than FPCA. Still, for the same reason, FPCA will lose the spatial information. And also, the Tucker works better than CP here. I think the reason is that Tucker allows different dimensionality have different rank, so it is more flexible. For a summary, we developed a penalized location skew regression model to use the degradation image stream to predict the IOL of a system. And we decompose the coefficient tensor using CP and Tucker, and developed two relaxation algorithms to estimate the model. And a simulation and case study showed that our model works well for both the precision accuracy and precising. Here are some references, and thank you. If you have any questions, I will be happy to answer. Yes.
Do your approaches belong to low-rank tensor decomposition?
Yes.
So CP and
Yes.
Tucker
Yeah.
are okay.
The assumption that CP and Tucker is that the coefficient tensor is low rank.
Okay. Sorry, another question. You talk about the third challenge, which is the failure threshold is hard to define.
Yes.
How did you define it in your simulation and case study?
Okay. So I'm saying that our model doesn't need the failure threshold because that for prediction part, we do not need to know the failure threshold. For the simulation and case study, for training part, we need to know the failure time. We use the failure threshold, but just for training part, it doesn't affect the prediction part. Yes.
Yeah, it is known that the FPCA requires your signals to share the same time domain,
Mm-hmm.
but your signals are typically truncated when failure.
Yeah.
So when you compare with the FPCA, did you do signal alignment or you just compare just with the regular FPCA?
Yeah, I'm glad you asked this question because I have backup stats here. So we use this time-varying structure. Basically, we only use the signals. This red line is the real-time test signal, and this long curve are the training signals. We only use the signal lifetime longer than the current test signals and cut the signals to share the same time domain.
So you ignore some signals?
Yeah, I ignore some signal in this part.
Yeah, yeah.
So in your simulation and the real data, you mentioned like you have temporal and spatial correlation.
Yes.
So the spatial, you mean image the data, right?
Mm-hmm.
Temporal, I haven't seen you how you put to the temporal degradation relationship in your simulation.
Oh, okay. So for the simulation, actually, we use the heat transfer process and here. If you look at this fuse here, it's going to, in time domain, it's going to gradually change. So that's the kind of correlation. If you plot each pixel, it will be a curve.
So what's that relationship? Is it stationary? How you simulate that time?
For this simulation, we use that heat transfer process. But no matter it's stationary or not, our model can work with that.
Okay, can you give some the intuition? What time FPCA will be equivalent to this tensor decomposition?
Let's say if the pixels are ID, there are no spatial correlation with each other.
Is it spatial or temporal?
Yes. So only if there are no spatial correlation, the FPCA should work equivalently with our algorithm.
So you mean the spatial is more sensitive to the result rather than temporal?
I think both of them are important, but the FPCA ignore the spatial one, so it's definitely going to lose some information.
Yeah.
Yes.
So I have a basic fundamental question. When you're looking at infrared data, right? And so it's a FLIR system, I believe. So it's an indium SB detector. These, right? Am I right in saying that's the equipment you are using? It's an Indian SB connector, right? It's a detector.
It's a
FLIR system, right? It's a FLIR system. Is a FLIR infrared system? Is that
Yes.
what it is? Okay.
Yes.
So now there is a problem with this system physically, that the projection, which way you're looking, is extremely important. With a bearing, you have a curved area, right? So what happens is your surface is not, the detector surface is not normal to the bearing curve, right? Because you're looking in one direction. So you always have that edge problem. That's the first thing. And as the bearing rolls, your detector starts to see some kind of a artifact, because you're heating, but there is also spread because of the effect I told you. So did you compensate for it or did you measure it? There are ways to measure it. So I would like to know whether you did that.
Okay, so the first question is how do we choose the area for the...
No, that's not what I'm asking you. I'm asking you that when you have an infrared sensor, you have to look normal to the area. If you're not looking normal to the area, you get an artifact. Okay, and that artifact usually happens around the edge. And as the bearing starts rolling and it heats up, the image starts to, it becomes worse and worse. So you might be recognizing an artifact rather than some kind of a temporal correlation. The way people do this is they use a thermocouple. Okay. But I'll leave it at that. So did you take that into consideration?
Yeah, actually, I think I should. We're not monitoring the bearing itself, actually. We're monitoring this motor that drives this.
Exactly, that's also curved area, right?
Yeah, but so because we have a cooling system, so the heat of the bearing cannot be captured. But with the degradation of the bearing, the resistance is going to increase. So the motor is going to hotter and hotter. So it can be used to indicate the degradation process of the bearing. Actually, we have a curve here to show this result. Because our testbed also equipped with a vibration sensor. So this is signaling from the vibration sensor, and this is from the energy intensity of the image streams. We can see that when the degradation happens, this temperature of the motor can also, capture the trend of the degradation.
Okay. Thanks. Next speaker will be Anna, and joint work with Dr. Chang Wang. Please.
So thank you for that introduction, and thank you all for attending this morning's very early session. I'll be talking today about model transfer via equivalent effects of working variables, and I'd like to begin by discussing the problem that motivated this research, which is quality control and 3D printing. So as we all may be aware, 3D printing is a disruptive technology that can have a great impact in manufacturing. It has a lot of potential advantages, but one disadvantage of 3D printing is the inevitable shape deformation that's introduced into manufactured products. And this is something that we've encountered in our specific stereolithography process. Whenever we would manufacture shapes, such as this flat cylinder right here, the product would deform. The boundary wouldn't be a perfect circle as we would like in the computer-aided design model. Indeed, what we observe is the product would shrink to form an ellipse. And so the question that we faced when we started this research, quality control for 3D printing, is how do we control this deformation? How do we change the 3D printer in some respect so that when we manufacture a product, it has the correct dimensions as specified in the computer-aided design model? And our initial strategy was to collect data on these 3D printed products. For example, manufacture multiple cylinders, maybe a cylinder of nominal radius 1/2 inch, 1 inch, 2 inch, and 3 inch. And for each point on the boundary of such a cylinder, measure the deformation, which is just the difference between the observed radius and the nominal radius, as specified in the computer-aided design model. When you could collect such data, hopefully you could form a statistical model so as to understand the deformation for these products. And from such a model, you can predict deformation and see how to change the original computer-aided design model, basically add or subtract material on the boundary of the shape to form a new CAD model, so that when that deforms, it deforms in the shape you want, a circle. And we've achieved some measure of success with this strategy. For example, when we started printing the cylinders in 2012, by adopting this strategy, by implementing a compensation plan to the computer-aided design model, we could reduce deformation by 1 order of magnitude. However, an important question that was raised during the process, during this research, is how general are these quality control strategies? If you could develop such a strategy for one setting of the 3D printer, can you hopefully extrapolate it to other types of printers, other types of stereolithography machines? And a problem that we encountered is that lurking variables, or unobserved factors that you can't really measure or assess, they're ubiquitous in 3D printing, and they have an impact on shape deformation. You need to account for those. So for example, what I have here is a picture of the stereolithography machine, and here are the 4 printed cylinders as before, the 1/2 inch, 1 inch, and 3 inch nominal radius cylinders. Now, when we manufactured these cylinders, we had some observed factors that we could directly control, specifically the compensation, the addition or subtraction of material on the boundary of the product. But lurking behind the scenes are variables such as overexposure, underexposure, different types of calibration settings that we did not directly observe, but during our process, they were controlled. They were effectively controlled. So we could form one statistical model to predict deformation, which is illustrated here. The dots are observed data, the bold lines are mean trends, the dashed lines are intervals, and by using that model, we could control deformation. This was in 2012. However, in 2014, what occurred was a technician came and changed the settings of the machine, and this is now the new deformation for cylinders manufactured under the settings of the 3D printer. As you can observe, the deformation profiles for the 2012 data are drastically different from the deformation profiles from the 2014 data. And therefore, the kind of models we develop in 2012, the kind of strategy we develop in 2012, cannot be directly applied to this new setting of the lurking variables. And we actually have no idea what the new settings of the lurking variables are. Previously, they were controlled because we were working with a controlled setting for a machine, but when the technician came in, he changed the settings in a confidential manner. We'll never know exactly how he changed the settings. So now, we can't directly apply that quality control strategy as before. The question we face is it possible to use that knowledge, to leverage all that knowledge and information that we had from the previous setting, so as to get started forming models for this new setting of the lurking variables, and hopefully transferring that knowledge and quality control strategies to this new setting of the lurking variables. So just to summarize, I want to summarize the big challenge that we face with lurking variables and the objective that I want to address in this talk. The challenge is that these lurking variables, or factors who are completely unobserved, frustrate the extrapolation of experimental findings across settings, because they definitely have an impact on the outcome, and so you can't directly extrapolate the model and quality control strategies developed under one setting of the lurking variables to other settings of lurking variables. And this is especially a big challenge for advanced manufacturing processes, such as additive manufacturing, where it's actually expensive to manufacture these products. As I've shown, we could work with 4 products here and perhaps manufacture another 3 products under this new setting, but for every possible setting of lurking variable, every possible setting of these 3D printers, we don't want to continue manufacturing a lot of case studies, performing extensive experiments so as to redevelop new models. We'd really like to transfer the knowledge we develop from one setting to new settings, and that's our objective. We want to address this challenge of transferring models and quality control strategies developed under one setting of lurking variables to other settings. Now, this problem has a rich literature. There has been some discussion on lurking variables and model transfer in the statistical literature, computer science literature, but from our understanding of the literature, these statistical and machine learning methods that currently exist don't satisfactorily address the challenge introduced by lurking variables. For example, in the statistical methods, typically focus on identifying the lurking variables, whether they actually exist or not. But once you identify lurking variables, there's no systematic way or approach to incorporate their effects in previously developed models under previous settings of lurking variables. And this goes back as far as the work of Short in 1931. He developed methods to identify the existence of special causes and hopefully make them assignable causes. But the general idea there is to perform much more extensive experiments so as to incorporate that knowledge into previously developed models and quality control strategies. And that's been followed up by work by Joyner and Cook and Critchley. They really, in the statistical literature, they just focus on can you identify the existence of lurking variables, not necessarily incorporating them into previously developed models. Indeed, when it comes to transfer learning, the computer scientists have a great deal of methods to offer. The specific type of methods fall under the class of inductive transfer learning methods. This is a branch of machine learning. And these methods generally proceed by reweighting data from previous settings, according to whether they improve or fail to improve learning in new settings of lurking variables. So basically, those data in previous settings that improve learning in the new setting are upweighted, and the data in previous settings that don't improve learning are downweighted. It's basically a reweighting strategy. However, these methods typically assume that you have a large amount of data in previous settings where you've actually developed models. And they don't actually provide explicit conditions on how the data is generated so that you can actually learn about the effects or the impacts of lurking variables on the model itself. So these are very algorithmic approaches, very deterministic, but they don't provide much insight into the physical process or how you could collect data to learn about the effects of lurking variables. And the most recent work on lurking variables and model transfer has been the work on transportability by Jadair Pearl and Ilias Barenboim. This work operates under their approach to causal inference, which is based on causal diagrams and the do calculus of Jadair Pearl. But these methods focus primarily on non-parametric inference for probabilistic dependencies between different factors and the response. And what we're focused on for quality control for 3D printing is on transferring parametric features of models across different settings of lurking variables. Because we view that a parametric model will provide much better quality control in general for these kind of advanced manufacturing processes. And another disadvantage of their approach is that they're also assuming you have a large amount of data so that you have solid knowledge about causal relationships between different factors in whatever process you're studying. So again, a major disadvantage for both transfer learning and the transportability methods of Jadair Pearl and Ilias Barenboim is they require a large amount of data. So our strategy to address this challenge of lurking variables in model transfer is to use this engineering phenomenon of effect equivalence. This was originally developed by Hui Wang and Cheng Wang in 2005. And the basic idea is this. When you manufacture a shape, or when you manufacture any type of product, under a new setting of lurking variables, and perhaps some setting of the observed factors, you could view those shapes as equivalent being manufactured in a previous setting of the lurking variables, but with a different setting of the observed base factor. That different setting is what's referred to as the total equivalent amount of the changed lurking variable settings in terms of that observed factor. In this case, for 3D printing, the observed factor is compensation. The observed factor is compensation. And what we view effect equivalence as being that if you have a certain setting of overexposure or other setting of calibration, you could translate those into the equivalent amount of compensation that will generate the equivalent type of shape. So that's what I'll be discussing in today's talk. I'll be discussing model transfer by effect equivalence and the Rubin causal model. So first I will formulate a general framework of effect equivalence under the Rubin causal model. The Rubin causal model is a general framework to discuss the causal effects of treatment factors on a response. Under this general framework, then I'll develop Bayesian methodology so that you can enable modeling of the total equivalent amount of lurking variables in terms of an observed factor, and thereby transfer knowledge and models from one setting of the lurking variables to new settings of the lurking variables. I'll be illustrating our approach, our framework, and methodology on two case studies for additive manufacturing. First one being accounting for the lurking variable of over or underexposure in 3D printing, and the other one being the change in the calibration setting that I mentioned previously. And ultimately, we can conclude that the synergy between engineering and statistics can effectively account for the problem of lurking variables and model transfer for more general contexts, medicine as well as other types of contexts. So I'll begin with some definitions first, describe our approach and the case studies and our methodology. So here are the first couple of definitions and assumptions. So I'm going to consider studies, either experiments or observational studies, on k factors, such that none of these factors are background characteristics or covariates. Furthermore, any factor is always either fully observed or underobserved, meaning that any factor is consistently defined as either a lurking variable or an observed treatment factor. And finally, I'm assuming that the level for any factor is not the outcome of a level of another factor, so that there are no linkages between different factors. That would require some more advanced statistics that's beyond the scope of the current presentation today. Okay. So the set of levels for a factor is denoted by script x sub k, and for any experimental unit, I'll be denoting its covariate vector by bold z. The covariate for these manufactured products could be, for example, the nominal radius or other such background characteristics for the 3D printer at that particular point in time. The potential outcome under any setting C1 to Ck of these factors will be denoted by y C1 to Ck. And just to simplify the notation in the presentation here, I'm going to present everything in terms of just one experimental unit, but these definitions apply to multiple experimental units. You just have to introduce subscripts to denote each experimental unit. So to proceed, let's first define what we mean by factor equivalence. What do we mean by a lurking variable being equivalent to observed base factors? So let's provide some models for the potential outcomes under different settings of the factors. So this model right here will denote the probability density function for the potential outcome under settings x1 and x2 of the first factors and some base settings for the remaining factors. And this P1 here is the probability density function or model for the outcomes under new levels x1 of the first factor and some base settings for factors 2 to k. And finally, this P2 is the probability density function for the outcome under any level x2 of factor 2 and some base settings of factors 1, 3, all the way to k. Now, by factor equivalence, all we mean is that for any base setting of the factors, C1 to Ck, you could find functions such that you could translate the effects of one factor, for example, factor 2, in terms of the equivalent amount of factor 1 in the base setting where factor 2, factor 3 are all held constant at C2 to Ck, and just factor 1 changes. So that's being illustrated here. We're talking here in this definition with respect to a specific model feature f. So the expected model feature under this setting where factors 1 and 2 can change is exactly equivalent to the same thing as the expected model feature where just factor 1 changes and factor 2 as well as the other factors remain fixed at their base setting. And the same thing holds for going the other way. So that expected model feature under different settings of factors 1 and 2 is equivalent to the expected model feature when the factor 2 changes, but factor 1, factor 3, all the way to factor k remain fixed at their base settings. So in this sense, when you manufacture a product, the change in a factor can be equivalently translated in terms of a change of an equivalent factor. Now, factor equivalence can be argued to hold in 3D printing in a natural way. In this case, the first factor, what we refer to as the base factor, is compensation. Basically, the addition or subtraction of material to the boundary of a shape. And one type of lurking variable is over or under exposure. In the stereolithography process, when light shines down on resin, it doesn't shine down directly as a straight line. It spreads out in neighboring pixels. And that can be equivalently viewed as adding material or subtracting material on the boundary of the product, as in here. So more formally, when you talk about the expected deformation for a particular point under a setting of compensation x1 and some exposure setting x2, that could be equivalently viewed as the expected deformation in this base setting where there is, in this hypothetical base setting where there is no over or under exposure, but the compensation changes to this equivalent amount that captures that over or under exposure in the setting that you're currently working with. So this is referred to as mean effect equivalence of over or under exposure in terms of compensation. And another case I'll illustrate this was previously mentioned. That is the effect equivalence of the calibration in terms of compensation. Now, when the settings were changed during the calibration process, it involved a lot more factors than just one. There were multiple factors. But we could view those changes in those factors in terms of an equivalent amount of the change of compensation in an original setting, in the 2012 setting where we had the original setting of those factors. So now what we're viewing is the expected deformation in that new calibration setting to be the equivalent viewed as the expected deformation in the previous setting, but with just an equivalent amount of compensation that captures that change in the factors behind calibration. So these are the two case studies that will illustrate our methodology on. And to perform this, this model transfer in the presence of lurking variables, all we really need to do is learn the total equivalent amount of the lurking variables in terms of an observed base factor. As long as we could learn this total equivalent amount, this t, then we could transfer this model developed under the previous setting of the lurking variables to capture the outcomes under the new setting of the lurking variables. And we'll do this learning under a Bayesian framework. It proceeds in 2 steps. The first is to use all the data, the previously manufactured data, and use the previous model, as well as the new data under the new setting of the lurking variables, to calculate the posterior distribution of the total equivalent amount of the lurking variables for units in the new setting. This is what we refer to as the exploration step. And the next step is the modeling step, using that posterior distribution of the total equivalent amount to formulate a model for it in terms of background characteristics as well as that observed base factor. And this approach, this general Bayesian methodology, will be valid for any randomized experiment or observational study that satisfies a specific unconfoundedness assumption, which is right here. We define a factor assignment mechanism in a setting to be mean effect equivalence unconfounded if the assignment of that base factor does not depend at all on the outcomes. So for any distinct outcomes, y and y prime, the assignment mechanism for that base factor remains the same. And this assumption holds true by design in randomized experiments, and it could be true in certain types of observational studies, which I could discuss at the end of the presentation. Under mean effect equivalence, we then have that the joint density of the observed outcomes and the base factor assignment decomposes as a product of their marginal densities. And this is useful for the methodology because now all we need to do is focus on this one term right here, this partial likelihood, in order to learn about the posterior distribution of the total equivalent amount of lurking variables in terms of that observed base factor. That definitely simplifies the inference for the total equivalent amount. Okay, so I'll illustrate the exploration and modeling steps for these first 2 case studies. So the first one is learning about over or under exposure. What I've plotted here are the posterior distributions of the total amount of the lurking variables in terms of compensation for 4 circles of nominal radius ½ inch, 1 inch, 2 inch, and 3 inch. Now, what you observe is that these, the posterior distribution for all these circles lie right on top of each other, which suggests that the total amount of exposure is not a function at all on how big the product is. And in fact, the range of these total amounts is fairly limited. It's only between 0.006 and 0.008 inches. So one reasonable approach to proceed to model this total amount is to assume that it's constant. By adopting this model for the total amount, that's basically just a constant factor, and fitting that model to the observed data, we see that it provides a good fit. And furthermore, we could use that for quality control. So this is the observed deformation profiles for the 2-inch and 3-inch non-radius cylinders. And by using this type of model for the total amount, we could form a compensation plan and apply it to a new cylinder of 2.5 inches. And we could see that we reduce deformation by 1 order of magnitude. We remove these harmonic trends, and we've effectively controlled for that lurking variable. Now, in terms of the calibration case study, what I've plotted here are the posterior distributions of the total amount for the 3-inch, 1.5 inch, and ½ inch nominal radius cylinders. And you can see that these are very systematic and simple to describe harmonic functions for the units. And furthermore, what's really interesting is that if you compare these posterior distributions to the optimum compensation plans that we've developed in previous work, there's a very nice correspondence. In fact, for the ½ inch, there's a very close correspondence between the posterior distribution and the optimum, whereas for the others, there is some type of discrepancy, but you can see it follows the same general pattern. So what we've learned is that when the technician came and changed the settings of the 3D printer, he did it according to a prior conception of what the optimum compensation is, but it was not exact. For the 3-inch and the ½ inch cylinders, it was not, the change in the calibration did not directly correspond to the optimum compensation plan, and that's what led to that residual deformation profile, the complicated deformation profile that you saw earlier. But by modeling this systematic trend in the total equivalent amount, we can now formulate a model for those 3 previously manufactured cylinders in the new calibration setting, and by using this model, in a very simple way, we could control the quality for these shapes under the new calibration setting, just by using the same methodologies before. So to conclude, the fusion of effect equivalence and the Rubin causal model, we believe, can address the challenge of model transfer across different settings of looking variables. And that was illustrated very nicely in terms of these two case studies on over or underexposure and calibration. It really helped us understand what kind of insights we could gain by using this methodology for these lurking variables, which are inherently unobservable and you can never measure them. And our methodology is applicable to a broader class of problems, statistics and look causal inference. Basically, any problem in which effect equivalence holds, and you could have mean effect equivalence unconfoundedness, you could apply our Bayesian methodology to learn about the total equivalent amount of lurking variables. And this also introduces broad new areas of research, which I could discuss offline. And I'd like to just conclude by thanking you all and noting that our work was supported by the National Science Foundation. So thank you all.
Yes, Dr.
Okay, so when you identify the lurking variables, do you require that the variable should be independent or not correlated with base variables?
So we're assuming that the base factor and the lurking variables have no effect on top of each other, on each other. There are no factor linkages. Now, if there is a linkage, if there is some correlation between these two, then you need to use some more advanced methodology from causal inference. One type is what's called principal stratification, and it basically allows you to account for the correlation between these two factors so as to get a better model for the outcome as a function of the two factors. Yes, so in this case, we're assuming there is no correlation, they're independent. The other case is a more advanced, it requires more advanced methods.
When using equivalence methods, usually it's equivalent, the system is equivalent to this one with respect to something.
Correct.
Do you have any insight into, when you make the equivalences, what it's, the things that are not captured by the equivalence?
That's a great question, and that's going back to, so that goes back to the future research. When you have multiple covariates and multiple base factors, it's hard a priori to say what's equivalent to what other types of factors. At this point in time, we haven't actually addressed that question, but that's definitely something we want to address in the future. Can you do some type of testing procedure to cluster the factors into different types of equivalent classes? Exactly.
Okay, I see.
Interesting presentation, generalization of this work. For example, look at the geometrical difference changes. Well, but that process will depend on the type of material depositing, the temperature, the multi-layer, the thermal changes, and so on.
Yeah.
How do you take that from a specific type of environment to more generalization when you have different layers, different thicknesses, and others?
Now, we've definitely, in previous work that Chung has done with his grad students, we've observed that, for example, the different layers, the thickness of the layers, definitely has an important impact on deformation. We believe that we could apply this effect equivalence as well by viewing the thickness of the layers in terms of an equivalent amount of compensation. So all I could say is, at this point in time, we do have some preliminary ideas about how to proceed. There are still a lot of factors we have to account for. It's much more complicated, so there's still a lot more work that needs to be done. Given the time constraints, do we have time for?
Yeah, I'll
Okay.
next speak.
Okay. Well, thank you all
We
again.
have no time.
We can definitely talk about it after the session. Be more than that.
So our next speaker will be Amir from Mississippi State University on additive manufacturing.
Good morning, ladies and gentlemen. This is Amir. I am a third-year PhD student at Mississippi State University. And today I will talk about my methodology, which is able to accelerate process optimization of laser-based additive manufacturing by leveraging information from prior studies. Additive manufacturing, colloquially known as 3D printing, has been labeled as a disruptive innovation. It's been featured several times by President Obama, and it's also featured on the cover of Economist Journal 4 times just within recent 2 years. Right now, additive manufacturing is evolved, commercialized, and applied in many industries. It's valued at more than $5 billion, and it's also expected to grow up to $20 billion by 2020. In this research, we focus on laser-based additive manufacturing, which is a technology which is able to fabricate 3D metal functional parts in a layer-by-layer manner. This technology is able to fabricate very complex geometries, like aviation engine. It's also able to fabricate parts with functionally graded materials. I mean, some materials with properties that vary in space and time according to desired functionality. It's also able to fabricate 100% customized parts, like patient-specific biomedical implants. So far, 5 categories of laser-based additive manufacturing processes are defined, like direct energy deposition and powder bed fusion systems. In this research, we focus on selective laser melting, SLM for short, which is a powder bed fusion system. In SLM, powder is deposited by a roller to form a bed. Then it's selectively melted by a moving laser as a heat source. This procedure will continue layer by layer, and eventually the 3D object is fabricated. Despite all the mentioned advantages of laser-based additive manufacturing, like selective laser melting system, this technology is extremely prone to defects, like porosity and micro cracks, as you can see over here in this part. In this research, we focus on porosity. Definitely, such defects are very important and could result in inferior physical or mechanical properties of the part. For instance, high porosity means low part density, which eventually results in short fatigue life of the part. And please note that this technology is extremely sensitive to material, process parameters, and experimental condition. For instance, just slight changes in process parameters or material cause significantly different amount of porosity in the fabricated part. Hence, there is an urgent need to identify process parameters resulting in optimum level of physical or mechanical properties of the part, like part density and satisfactory level of quality. But what are the major challenges of laser-based additive manufacturing process optimization? First and foremost, a large number of factors contributes to the process. For instance, you can see here laser power, laser velocity, layer thickness, and powder morphology. The effect of these parameters are somehow dependent and coupled. Second, behavior of laser-based additive manufacturing processes is not well understood thus far because of very complex underlying thermomechanical processes. So the relationship between process parameters like laser velocity, laser power, and the part mechanical properties like part density is unknown. So we don't have any functional form of objective function to optimize. Most of existing methodologies are not suitable in our case because they either need functional form of objective function like common optimization methodologies, which is not the case in additive manufacturing, or they require a large number of experimental data to construct meta models representing objective functions as our target, like design of experiment methodologies, which is not the case in additive manufacturing because of extremely high experimental costs, specifically in laser-based additive manufacturing. Here, I've summarized some of the existing approaches. First category of methods is physics-based methods, which are developed based on differential equation governing underlying thermal process. They are extremely computationally expensive, so they have been mostly applied to very simple shapes, like thin-wall or coupons, which is not the case, again, in additive manufacturing, because we are interested in very complex geometries. Second category of methods is data-driven methodologies as opposed to physics-based methods. Under this category, we have traditional design of experiments like full factorial design. Most of these methodologies typically require a large number of experimental data because they can't account for the purpose of optimization. Another subcategory is sequential design of experiments methodologies, like minimum energy design developed by Dr. Dasgupta. Most of these methodologies cannot directly incorporate prior information and similarities among the systems. So when the experimental condition changes, we have to begin from scratch. In this research, we developed a novel sequential methodologies based on minimum energy design, which is able to accelerate process optimization of laser-based additive manufacturing by incorporating and leveraging information from prior, similar but non-identical processes. And again, please note that functional form of objective function is unknown in our research, and we are conducting extremely expensive experiments. I would like to mention that we verified our framework in addition to simulation studies by a real-world case study to maximize density of stainless steel parts fabricated by SLM system. And please note that this methodology is not limited to SLM system or part density or a stainless system. It can be readily modified and applied to other additive manufacturing processes, other mechanical properties, and other materials. To illustrate the advantage of our methodology, let me begin from traditional design of experiments like full factorial design. Here, X represents a process parameter like laser power. F of X is an unknown function representing quantity of interest like part density in the current study. These methodologies are one-time experimentation, and they typically result in large number of experiments. And also, the results cannot be directly extended to other processes. Sequential minimum energy design is a new methodology developed by Dr. Dasgupta. It makes a direct analogy with fundamental electrostatistics law, where the total potential within a system is proportional to particle charges and their location. This methodology assigns a positive particle charge to each design point in order to balance optimization and space filling properties. But how? For instance, in this simulated example, the objective is to maximize part density, given two process parameters, laser power and layer thickness. This methodology assigns higher charges to design points with more potential of resulting in lower density and vice versa. Based on a very fundamental physics law, particle charges will push each other apart to minimize the total potential energy within the system. So instead of equally spending all the resources, by applying minimum energy design, we are able to spend more resources on the regions with more potential of resulting higher density. Even though sequential minimum energy design represents improvement in terms of saving experiments compared to full factorial design, but they both share a very important drawback, which is the fact that they cannot incorporate information from similar but non-identical prior studies. So when the experimental condition changes, we have to begin from scratch. It's a very important drawback because usually literature is full of valuable data that unfortunately we cannot directly incorporate them in our new process. Our methodology characterizes and iteratively update difference between prior and similar studies. For instance, here, black curve represents part density, unknown part density function in the current study. And red curve represents part density function in a prior study. They are not exactly overlapped because of some differences in experimental condition. U represent a part density reported by prior study. And capital Y represent corresponding part density in the current study, which is unknown. The difference between them is characterized by a random variable lambda. We call that difference of responses between prior and current study, or DRPCS for short. In this research, we are interested in deriving posterior distribution of lambda using available information. Let G represent posterior distribution of lambda given collected data from the current study represented by lowercase y. Pi, we are estimating this expression using Bayesian formula. Pi here represents prior distribution of lambda, and L represents likelihood function of lambda given y. We assume that DRPCS terms or lambda terms are independent normal variables. So the prior distribution can be represented by product of their PDF. The parameters of the prior distribution can be determined by domain or expert knowledge. Likelihood function has the same expression of PDF of y given lambda terms and available information. After extensive calculation, we found out that it's proportional to this expression. And eventually, we found out that posterior distribution follows multivariate normal distribution with this mean and covariance structure. They only depend on prior parameters and data from current and prior studies. The sequential procedure can be found on this flowchart, but to make it easier to understand, let's just see this animation. Here we have 3 prior reported data from 2 different prior studies, blue and red dots. Green dots represent collected data from the current study. After applying modified version of sequential minimum energy design methodologies, we collect data from current study, and we use them to update posterior distribution of lambda. So, schematically, the prior data move toward the black curve, and eventually we are able to find the highest density by very few experimental runs, because we are leveraging prior information. To validate our framework, we have conducted both simulation studies and case study. First, I would like to present simulation studies. We have tested how different characteristics of DRPCS term can affect our methodology performance. First, we generate part density data using this empirical model, which is a function of laser power, laser velocity, hatch spacing, and layer thickness. To generate prior data set, we artificially induce some errors to calculated part density data from this formula. We evaluate the performance of the method by comparing required number of experiments to achieve a targeted density, which is set to 99.65 in this case. We developed 5 different scenarios, including different number of prior data and different characteristics of DRPCS. For instance, in some of them, we can see negative DRPCS, positive DRPCS, small magnitude of DRPCS, so on. We benchmark our methodology against full factorial design. We can see that our methodology has at least 75% improvement in terms of saving experiments compared to full factorial design in all scenarios. Then we benchmark our methodology against sequential minimum energy design. We see consistent improvement in all scenarios. But when the DRPCS magnitude increases, our methodology performs greater. And the largest improvement can be seen on scenario 3, when we have both positive and negative DRPCS. It may occur when the prior data come from different resources that might contradict each other. In the case study, we targeted at maximizing density of stainless steel parts. We used stainless steel PH74, which is very well-known material because of its mechanical strength and porosity resistance. Our collaborator at Texas A&M is working on this material for many projects in collaboration with several institutions like Sandia National Lab. We found 3 prior studies, including part density data. And as you can see easily here, the experimental condition is not the same as in our study. For example, powder morphology is completely different. We used the reported part density as our prior data, and we applied our methodology to maximize part density. And we achieved 99.22% relative density of the part at the 6 experiments with these process parameters. We stopped here because it's the setup recommended by the manufacturer. In summary, we developed a methodology which is able to accelerate process optimization of laser recycling manufacturing by leveraging prior information from similar but not identical studies. In addition to simulation study, we have conducted a real-world case study, and we achieved a target part density with relatively few experimental runs. I will be more than happy if you have any question, and thank you for your attention.
So I have a question. In your experimental results, you used cases where there are only 2 or at most 5 experimental points available. So is that typical of the actual settings, or are there generally more points available from prior studies?
You're talking about a real case study or just actually?
No, the simulated case study that we did.
Okay. No, for example, in real world, for this real world case study, we found 3 prior studies. Each of them include, for example, 10 or more than that reported data. So I just actually...
Yeah, so that's what I was thinking. So you might have 20, 30 data points.
Yes, exactly.
Your experiments were all based on only 2
Actually, it's just illustrative example. I just make that figure to show the concept.
Okay.
But it's not real world simulation.
Thanks.
So in your case, right, if you are using prior studies, right?
Exactly. Right.
So if your current study is similar to some prior studies, your system, maybe your model may get better performance.
Sure.
Right? So I'm saying that, but it depends on the case by case. Your model looks like.
But actually, the major contribution is that the experimental condition in those prior studies are not exactly same as the experimental condition in our study. So the contribution of this work is capturing similarity among the different processes in order to facilitate our process optimization.
Okay, I think.
So one more question from
I'll just continue to these comments. Do you need to have some pre-requirement between the prior experimental condition data and your current experimental data to make your method more effective?
Actually, this is what our procedure is doing. After collecting data from the current... No, there is no requirement. I mean, there is no specific assumption or something like that, because after collecting data, we are up to, the only requirement is estimating the prior distribution parameters, which can be determined by expert knowledge.
So their randomness distribution should follow the same.
Exactly.
Our next speaker is Liu Xiao from IBM.
Okay, good morning. It's my pleasure to be here today and share with you our recent work on the statistical modeling for spatial temporal damaging data. So spatial temporal dimension model arises when data are collected from over space and time, and we need to address both the temporal and spatial correlation. And for many real problems, and this can be very extremely challenging. So at the beginning of this presentation, I'm going to start with two motivating examples. The first example is about autocatalytic degradation in polymer microspheres. So the physical dimension model, as you can see, can be described by a partial differential equation here. So the C is the degradation in this context. It's actually the change of the concentration of the autocatalytic. So basically you can see, in this case, the degradation does not only depend on time, it also depends on another parameter, R. R is the location index. Basically, it's the distance to the center of the microsphere in a spherical model. So this physical model fully specifies how the degradation evolves over time at different locations. If we look at that figure at the bottom, you can see three curves. That's the degradation path for different values of R at different locations. That means for spatial temporal degradation data, sometimes we need to deal with completely degradation patterns or paths at different spatial locations. The second modeling example is actually modified from my previous work with IBM, so I think it's a good illustrative example. So it's about the degradation on the surface. So what you see here is the degradation measured at 9 equally spaced time intervals. And in this case, at different time intervals, so you can see that the degradation obviously starts at time 3, and it's getting worse as time goes by. And probably, you've already noticed that there's a very important phenomenon for many spatial temporal degradation problem is the degradation propagation in space. So you can see that in this case, it seems that the degradation propagates from the south to the north direction. And this is something we need to address in our model. So throughout this presentation, I'm going to revisit these two motivating examples from time to time. Here's the outline of this presentation. So I'm going to start with introduction, and talk about the challenges to be addressed, and then I'll present you the main results and some key results, followed by a simple numerical illustration. Degradation data provide a rich source for reliability analysis because failures are very difficult to obtain. Even in the age of big data, we have data from various sources, but that does not mean we can easily obtain a lot of failures. So because of the importance of this degradation modeling, so in the past 20 years, there's so many excellent work being published in this area. I cannot even possibly name them all. So if you look at the available approaches which are out there, one important modeling approach is to describe the degradation process by a stochastic process. And then if you look at these methods, most of them share a common assumption, which is known as the additive accumulation of degradation. Basically, it says that every increment of degradation can be seen as a superposition, additive superposition of a large number of independent and stationary small increments. So it is precisely because of this assumption that makes the family members of the Levy process popular choices for degradation modeling. For example, gamma process and Brownian motion process. So in this work, we're concerned with the modeling of degradation data, which are not only collected over time, but also a spatial domain. So just imagine that if we follow the existing modeling approach, so naturally probably what we can do is just to extend the stochastic process, pure time-dependent stochastic process, to space-time process. That means we're looking for a spatial temporal random field, and we hope that this spatial temporal random field can be used to approximate some spatial temporal degradation process for some real problems. So our knowledge, this problem has not been well studied. Now firstly, let's take a look at what the challenges are. So the first challenge is that we need to address the spatial dependence and spatial propagation. Sometimes the spatial dependence is known due to the underlying physical mechanisms, but most of the time it's not known and needs to be established through statistical analysis. The second challenge, spatial heterogeneity. Basically, it means that at different spatial locations, we may have, very often, we're dealing with different degradation patterns. Like in this case, at different locations, A, B, C, D, E, we have actually completely degradation patterns. This is very common. So because of these two challenges, just imagine that if we're trying to model this process by some random field, that spatial temporal random field, most likely, it's going to have a very complicated spatial temporal covariance structure. For example, very often it's going to be anisotropic. That means we do not expect similar properties along different directions. Second of all, very often it's going to be space-time non-separable. So because of this, when we're given a data set like this, it's going to be very difficult for us to even guess sometimes or envision how the covariance structure will be. The fourth challenge, computational cost. Sometimes the spatial temporal data set can be huge. Just imagine the image data. And of course, the number of unknown parameters to be estimated sometimes can be huge too. In this particular example, later on you'll see that we have more than 10 parameters to be estimated. So let's see how this problem can be addressed. We're going to start with a degradation process which is continuous in time and discrete in space. Later on we're going to expand this. So Y here represents the degradation at location S and time t in a d-dimensional space. To make this presentation easier, so I'm going to assume that d equals 2. But the results can be extended to a higher dimension when d equals 3, and also it includes the special condition when d equals 1, just as in the first motivated example. And recall the assumption of additive accumulation of degradation. We're going to assume that Y takes a general additive form. So basically, Y can be written as the sum of two sub-processes, a generation process and a propagation process. Both processes are stochastic process. The generation process basically is a spatial process. It captures the amount of degradation generated at location S in a time interval from t minus delta to t. And as many statistical models, we're going to assume that this G can be written as a sum of a deterministic term and a random term, epsilon. So the epsilon here is actually a spatial process with its covariance function proportional to the length of that time interval, delta. And C here is a covariance function for some waiting time spatial Gaussian spatial process. Later on in the numerical example, we're going to try different assumptions for this C, and we're going to pick the most appropriate one. And the key, the interesting part is about this propagation process. The propagation process is a space-time process. It depends on the degradation at the previous time, t minus delta. It is used to capture the propagation of degradation in both space and time. Generally speaking, it is this term that actually introduced the spatial dependence into our model. How can we model this? In this work, we're going to use a convolution model to capture, to mimic, to approximate the spatial propagation. So basically what you can see in this equation, the propagation is actually, the z is obtained from the degradation at the previous time, y at t minus delta, through a convolution operation. Omega is the convolution kernel. We have a scaling factor here, zeta. Zeta we assume that's less than 1. Basically that means lambda is a positive constant. Later on you'll see that this condition guarantees that the random part of the degradation process can be approximated by a weakly stationary process. Later on we'll see that. Okay, since convolution operation is essentially a linear operation, so equation 4 basically implies that the propagation is obtained through a linear combination of the degradation in the neighboring area at the previous time weighted by some spatial kernel function. Theoretically speaking, any infinitely divisible functions can be used as a proper spatial kernel function, such as gamma density function or Gaussian density function. But in this work, we assume we're going to use a Gaussian density function, and there's a reason you will see. So this Gaussian density function basically has a mean and covariance denoted by mu and sigma. Now, think about this. We're going to use this convolution to capture the propagation. So naturally, we must allow this mu and covariance, both of them, to depend on the propagation of degradation. Specifically, let v be the propagation vector. That means this v tells us the speed and direction of spatial propagation of degradation, and then we're going to adopt the following parameterization. Mu, as you can see, is basically the distance traveled within a time interval along the direction of propagation. Covariance matrix sigma also depends on v, the propagation through a proper rotation matrix. R, we're going to parameterize this rotation matrix R such that rho 1 and rho 2, they respectively control the standard deviation of the convolution kernel parallel and perpendicular to the propagation direction. So this is how the assumptions we made about this convolution process. Now, let me give you some very intuitive, two toy examples to see why we can use convolution to approximate the propagation process. This is a one-dimensional case. The horizontal axis, that's location. You can see a blue arrow indicating the direction of propagation. So if I play this, this is basically what you see here is basically a sequence of convolution operation. It seems that we can use this convolution operation to approximate, the propagation along the x-axis direction. In a two-dimensional case, we have the same story, but this time the propagation is from the southwest to the northeast. This is the initial condition. After we perform one operation, convolution operation, this is what we have. If we repeat this process for many times, it seems that right through these two examples, we can see that convolution might be, I'm not saying it's the only way, might be used to approximate the propagation phenomena. But now, next, I'm going to show you why it's a good choice. The reason why it's a good choice, simply put, we can show that by assuming a convolution with a Gaussian kernel, we can establish the relationship between a statistical diversion model and some physical diversion processes. If you look at physical diversion process, very often it's defined by partial differential equations. In the first motivating example, we've already seen that. This is the physical diversion process for the autocatalytic degradation. It's two terms on the right side, a reaction term and a diffusion term. But let's consider a more general case. Let's consider a partial differential equation like this. This is called the scalar transport equation. It has four terms on the right side: reaction, convection, diffusion, and decay. So basically we can assume that under this condition, if the degradation propagation is uniform and steady, that means the propagation does not change over space, does not change over time. The solution to the scalar transport equation can be written in this way. Just look at this equation. On the right side, two terms, a generation term, and the second term basically captures the convection, diffusion, and decay of degradation basically through a convolution operation with a Gaussian kernel. So if you compare this solution to the physical model, to our proposed statistical model, the similarity is immediately seen. But there's a key difference that our model is a stochastic model. The physical model is actually a deterministic model, and the relationship can only be established under certain conditions. And we can further assume that, basically show that, if the diffusion is small enough, can be ignored, maybe the decay can be ignored too, the generation term, the deterministic generation term in our model actually is a good approximation to the reaction term in the physics model. So this result allows us to establish the relationship, which I think is a very important relationship between physics and statistical model, which helps us to build a physics-based statistical model if necessary, which I personally think is very important for solving an industrial problems. Now, having made all the assumptions, now we're ready to write down expression for this different process. Basically, we're going to further divide this time interval into a number of n smaller time intervals, and we have this expression. Three terms on the right side, all of them have clear interpretations. The first term on the right side, it's a deterministic term. It captures the amounts of degradation generated over the time interval between time of t minus delta to t. The second term is a random term. It captures the certainty associated with the generation process over the time interval. The third term is also random. It captures whatever happened before time minus delta. So immediately you can see that this is going to be a non-stationary process in a sense that both the mean and variance, they change over time. So that means it's going to be very difficult for us to derive the covariance structure. So again, we rely on approximation. Basically, we can show that if we let n approaches to infinity, and remember this condition lambda is larger than 0, that means the scaling factor is less than 1, we can actually approximate this divergent process by using a simpler expression. Now it has two terms on the right side. The first one is deterministic. It's not going to affect our covariance structure. And the second term now it's random, but now we can see that it's actually a weakly stationary process, second order stationary process, meaning that the covariance only depends on the separation of time and space. So we can make our life easier in that way. Now we're ready to derive the covariance structure of this divergent process. Basically, this covariance function fully characterizes the property of this proposed stochastic divergent process. Okay, We can also derive some nice properties of this model. Let me quickly show you what they are. First of all, our model has we can show that this model actually has a linear representation as long as the generation term can be written as a linear function of some covariance. It's always nice if we can see a linear representation because, for example, if we want to do parameter estimation, we can use least squares. Although I'm going to show you we don't want to do that because of the computational complexity. And this result is not surprising at all because if you think about it, convolution operation is actually a linear operation. So no matter how many convolution operations we perform, eventually we're going to end up with something which is linear. And also we can derive the derivation process which is continuous in time and also continuous in space. Basically it's obtained through a sequence of convolution over both space and time. Now next, this result is interesting. Basically it shows us how this proposed model connects to whatever we already have available in the literature. So basically, if you look at existing derivation models, many of them can be described by a stochastic partial differential equation like this. Two terms on the right side. The view is a deterministic degradation rate. And the second term B, that's a random term. For example, it could be a Brownian motion, could be a gamma process. It turns out our proposed model also has a SPDE representation. Again, it has three terms on the right side. All of them have very clear interpretations. The first term, U, deterministic degradation rate. Second term is interesting. That's the amount of adjustment we need to make to the degradation generation rate due to the spatial dependence. This term will vanish if we ignore the spatial dependence. It needs to be there if we want to incorporate the spatial dependence. The last term is a random term. Tau here is a spatially correlated Brownian motion. Now, just one remark on this. If you look at this, this is basically a stochastic partial differential equation. If you remember that we assume that the scaling factor is less than 1, basically that condition ensures that this partial differential equation has a stationary solution. So that's why we need to make that assumption. That's why we can approximate the derivation process by a weakly stationary process. I'm talking about the random part. Okay, this results leads to two conclusions. One, our model includes, basically if the spatial propagation and decay can be ignored, our model incorporates, basically becomes a multivariate linear process model. That means if you look at the degradation at any location, the marginal degradation process is going to be a Brownian motion process, which has been widely used in the literature, studied in the literature, and in practice. Now, okay, now I guess I have like maybe 2 minutes or 3 minutes. I can quickly show you a numerical example. In this numerical example, I just want to focus on two things. One, the parameters can be estimated by MLE. Two, the model can be validated by data. I won't go into the details. I'm going to use the second motivating example. As I said, there are a lot of unknown parameters to be estimated. Because our model has a linear representation, we can always use least squares to generalize least squares to solve the problem. But we don't want to do that. The trick is that instead of building the likelihood function based on the original observation, we're going to focus on the difference between the white tilde, which is the difference between y and z. We can show that this white tilde is actually a white-in-time Gaussian process. This allows us to quickly obtain the likelihood function, but this white tilde now actually depends on unknown parameters. Two remarks here. If you look at the computational complexity, computationally it's going to be complex, but if you compare it to generalized least squares, it's going to be much faster. And second, it can be easily parallelized, and we have to do that. Okay, now this is the estimation results for different parameters, assuming different parametric form for this C. I'm going to assume exponential spatial covariance function, Gaussian, and mountain. So this basically, I can see the estimated numbers. So let me just take a look at this, a few of them. Look at this V. So the second component, the V, is much higher than the first component, the V. We have already observed that the depth of propagation is actually from the south to the north. So we kind of expect this already. If you look at row 1 and row 2, they control the standard deviation of the convolution kernel parallel and the perpendicular to the propagation direction. So we expect row 1 to be larger than rho 2. Okay, this is basically the covariance plotted covariance function. It has a shape because of the propagation from the south to north. Okay, last slide. Model validation. It turns out we can easily validate the model by analyzing the residues. The way we can do it is that we can graphically compare the empirical variogram of the residue obtained and also to the theoretical variogram of the residue. So if you look at this, we can see if C is actually a Gaussian covariance function, we actually have the best fit among these three. So this brings me to the conclusion slides. So in this work, we have developed a statistical divergence model for spatial temporal different data. So if you look at how we view this model, we follow the existing modeling approach. We're looking for a spatial temporal random field. And we start with making assumptions. For example, the additive form, the convolution with a Gaussian kernel. And then we rationalize or justify, motivate the assumptions by establishing the relationship between the statistics model and some physics. And then we derive the covariance function. We derive some nice properties of this model, but then we apply it to a real data set. We validate it using data. If you look at this approach, it is slightly different with how traditionally a divergence model or maybe a statistical model is viewed. Because traditionally, when we build a divergence model, we can start with making assumptions on the covariance structure. For example, we assume this is a Gaussian model. This is a Brown motion model, and then we validate it using data. But here, for a complicated divergence process, spatial temporal divergence process, we simply cannot do that. So there's a reason we adopt this approach, and we believe this framework provides us with something, an alternative approach to model a complicated spatial temporal process, and it also is a good demonstration of how a statistical divergence model can be viewed based on both physics and based on data. So I hope you enjoyed this presentation. Thank you.
So can you talk a little bit more about how you model the propagation vector? Can it in fact change over time, or is it fixed in direction and magnitude?
Very, very good question. In this work, because we want to approximate using a stationary process, so we assume that the propagation does not change over time, not at all. Not over space, does not change over. But the framework can be extended. That's what I'm working on. I can even show you this. If it changes over time, see the propagation initially is from the west to the east.